In this video, we're going to start exploring differential equations. So what do we mean by differential equations? Well, put simply, this is an equation that involves some unknown function, as well as its derivatives, the derivatives of that function. So that could be a definition you think of, but I think what's more helpful is if we think about an example. So let's say I have a function y of x. So we don't know what this function is. It's an unknown function, but we do know that it's some function of a single variable x. Then we could think about its first derivative and maybe its second derivative. So again, we don't know what they are. We are just writing some arbitrary function like this. Now a differential equation then would look something like this. We might relate all of these by saying that the second derivative is equal to 3 times the original function plus the first derivative. Now this is just an arbitrary differential equation. I don't know if it is a physically possible one or not, if this relationship could exist. However, that's not the point here. The point here is just to show you at its core what a differential equation is about. Now I think before we get into the specifics with these types of equations, let's just think about an extension to this in real life. Why are we even looking at this? And actually it's very applicable. So let's think about Newton's second law. So hopefully you are familiar with this. This is not supposed to be a physics video. I'm just using this equation as a means to show you differential equations in action. So Newton's second law is really that the force is equal to mass times acceleration. So that's not what I'm too interested in, but I want to connect this to differential equations. So we have the force equals the mass of some particle and then its acceleration. Now let's think about this in terms of a differential equation, and let's say the core function that we're looking at, that unknown function, is the position function x of t. Now, let's just be very clear here. Earlier I was using y as being the function, so in other words the dependent variable you could think of it as, and x was the independent. That was the true variable. When I'm using this equation, because I'm just trying to stick with physics notation, the t, the time, is now the independent. So just keep that in mind. The x here is actually the function itself, is x. Okay, so now using this position function, let's rewrite Newton's second law here. So let me start with the right side. So mass is just mass. That's you could think of as a constant. That doesn't depend on the position. But what's acceleration? Well, acceleration is obviously the second derivative of position. And now what is force? Well, force you might think is a constant, but it actually does depend on position, and actually more than position, it can also depend on velocity. So in reality, the force function could depend on t, x, and it could also depend on x prime of t, which is, in other words, velocity. The point here, though, is that not only do we have the independent variable and the dependent variable x, we also have its derivatives. So don't get too caught up on this f here. This is just saying whatever the force function is. Maybe it's, for example, x squared or something. Whatever the force function might be, these are just, so here, these are just all of the different inputs into that function. Now, I just wanted to explain that to you just so you have an understanding of why we're even talking about this. So now let's go into a little bit more detail. So there are 3 main ways to classify a differential equation. And I think if you understand the differences between each of the possible categorizations, it'll help you when we are looking at this further. So the simplest thing to think about would be to think about the type. Now, what do I mean by type? Well, I'm going to show you. So, we usually have an ordinary differential equation. So by differential equation, I'm just going to say DE. So we could have an ordinary one, and we can also have a partial one. And what does this mean? Well, for an ordinary differential equation, this means that we would have some function y that depends on only one variable. So the unknown function that we're talking about, and then we were looking at its derivatives and so on, that function is only a function of one variable. It doesn't depend on more than one variable. And so if we have a case like that, then we are looking at an ordinary differential equation. So for example, we might see something like this, y prime equals y. And if we see something like that, we know it's an ordinary differential equation. How do I know that? How do I know y is only a function of x? Well, assuming we're using proper notation, we know that this is not the notation for a partial derivative. And I'm going to show you that in a second. So because of that, we know it's an ordinary differential equation. Now, by extension, of course, if an ordinary was only of one variable, then a partial one we would think of more than one variable. So we might have that some function u is equal to u of x and t. It could have more too. It's not necessarily only two, but I'm just putting it here just so we can see it. So any more than one variable, or one independent variable, I should say, the variable that's going in the function. And so what's an example of this? Well, we would know of a partial differential equation because we usually would see something like this. Partial u, partial x would equal, for example, the second partial derivative. Now, don't worry if you don't know what partial derivatives are. That's okay. That we're not really going to be spending too much time looking at them. But I just want you to have an understanding of the differences between an ordinary differential equation versus a partial one. But we're going to be focusing on ordinary differential equations. Now, I said there were three different types. So let's think about the second way of categorizing differential equations. And that is by their order. So what is meant by their order? Well, it's actually very simple. The order of a differential equation is equal to the number of the highest derivative in that differential equation. So this is the number. So in other words, is it the second derivative, is it the third derivative, etc.? So it's the number of the highest derivative. So that's what the order is. So let's just think about two examples quickly. So let's say we have y prime is equal to y squared. Now you might be thinking, is this the second order? But remember, when we are talking about the order of a of a differential equation, we are looking at the derivative. Here, it's the function squared, but the function that we're squaring is just a y. Here we have the first derivative. So really, this is first order. Now similarly, we could say y triple prime is equal to sine of y plus x. Now, don't worry about the x. We're looking at the derivative, right? The function. So here again, even though we have the sine here, the y here is still just the original function. It's not any derivative. So the order would be the third order. Here is the third order. And the last thing to think about is the linearity of a differential equation. So whether it's linear or not. So let's think about that. So we're going to think about the linearity. So this might seem complicated, but it really isn't. Just to keep this simple, I'm going to be thinking about a first order differential equation. So that means that we're only thinking about the original function y and its first derivative. But remember that doesn't really matter. We can extend this further if we wanted to, but let's just think about the first order case right now. What would a linear differential equation look like? Well, let's think about what we mean by linear in general. When we were just thinking about simple equations of lines, we would say something like y equals mx plus b. And so we say this is a linear equation, but to be more specific, this is a equation that is linear in terms of x. It's linear in terms of x. And what that means is we are not really doing anything to the x in terms of like squaring it or square rooting or putting it in a sine function or so on. At most, we are just multiplying it by some constant m, and then we are adding something after. That doesn't really matter either. So if we are following a pattern like this, then we would say it's linear in x. Similarly, if we are thinking about linear differential equations, we would see something like this, for example. We would say that, for example, y prime is equal to a of x, y, plus b of x. Now, I could have written this differently. That's okay, in terms of like where I put the y prime and the regular y and so on. But the point here is that y prime and y and whatever other derivatives we have are all related to each other linearly. So even though we could have a function of x here, like a sine of x or cos of x or x squared or anything, that doesn't matter because we're not thinking about x. But if we had a y squared, now that would not be linear in y. So let me just put that down here, what I just said. A nonlinear differential equation would be, now there you can't really write a general equation for this because there could be so many different possibilities. But for example, let me just write something here. We have that y prime is equal to sine of y. Now, here, even though we still have y prime and we have a normal y, that normal y here is within a function. It's a sine of y. And so that's not linear that's not a linear differential equation, and it's not linear in terms of y because it does not follow this pattern of linearity. Okay. Now the final thing I want to talk about in this video is what we mean by, before I get to that, actually, let me just review what we were just saying. So we have three ways of categorizing any kind of differential equation. We can think about its type, if it's ordinary or if it's a partial differential equation. We can think about its order, whether it's first order, second, third, etc., the highest derivative. And then we have linearity, whether it's linear or not, and how to recognize that. Now let's just think about the last thing that would kind of be important as an introduction, is how to solve these. So what do we mean by a solution? What is a solution of a differential equation? Well, remember, we have a differential equation that's relating some functions like y of x and its derivatives, for example. So let's just say y of x. Now, we might have y's and x's and y primes and so on inside that differential equation. But we don't actually know what y of x is. We are relating it to its derivatives, but we don't know what it means. And so the solution of a differential equation is to use the relationship that's given to us between the original function and its derivatives and figuring out what that function could be and what it is. Now, when we think about this, it might not immediately pop out at you, but you could think of a general solution, because when we take a derivative of a function, oftentimes a constant gets lost, right? Because if we took a derivative, then we got rid of the function. So even if the original function had a constant, you might not realize it did. And so we have an arbitrary constant, kind of like when we're taking an integral, we have an arbitrary constant. And so that's what we mean by a general solution. There is some arbitrary constant. And so what does that mean? Well, that means we are going to generate a family of possible solutions. That's another way of calling what we're getting here. A family of solutions, because we don't just have one specific solution, that's it. We could change the constant and we can get a lot of different options. Now that's in contrast to a particular solution. And what is a particular solution? Well, a particular solution is exactly what it says. We have just one solution. And how do we get that? usually we are given some information about the function. So it might be a point, or it might be something else. Or in other words, it could be more than just a point. That depends on the order, and we'll look at that later. But if you're given some information about a function, then you can narrow it down. And this is pretty much similar to what we were thinking about with integrals, right? If we just take an integral just given a random function, then we would have an arbitrary constant. But if we were given a point that's on it, for example, we might be able to solve for that constant and then determine a particular solution for that integral. Same thing here. If we are given some information, like a point, for example, we are probably going to be able to solve for that constant, that arbitrary constant.